Let us have a small look at this min hash idea and MASH distances that we are going to compute in this course. And I have to say that this this idea of min hashing is really one of the big new ideas, I would say, in genomics in general. So this is really something that is worth learning a little bit about. K-mers and Jacquard index is the first thing I will have to talk about, because Jacquard index is very central here. The MASH distance between genomes, let's see how this is defined actually. And then the min hash idea, which is actually how we compute this Jacquard index actually, which is part of the MASH distance formula. I will also mention briefly the extension to read sets, because we start out by comparing genomes. That's sort of the setting that we start out with, but exactly the same idea can be used for any sets, really. It doesn't have to be genomes. So read sets can also be, it's sort of meaningful to compute a MASH distance between read sets as well. And in that respect, the idea is the same, except for one thing, which is this Bloom filtering that I will just briefly mention. And here is the original paper. Have a look at this one. And it's actually a good idea to have a look at this one before you listen to my lecture here, because I will use stuff from that publication. I will use their same notation. You will recognize some formulas and stuff. And then you listen to my talk here, and then you can read it again to see if things become more clear. So the setting, we have two genomes, G1 and G2, right? And these have some common ancestor. So we assume that these two genomes are actually quite similar, right? And I can say that right away, that this MASH distance is actually only meaningful to compare rather similar genomes. If the genomes are very, very different from each other, you can still compute a MASH distance, but it will be very unreliable and not very useful. So this is for comparing closely related genomes, you could say, but yeah, at least fairly close, right? We also assume here now that both the genomes are of the same size. And this is not really a requirement. You can see my footnote here. They can easily be of different size. The only reason we have a common n here now is to make things simpler in the formulas and so on. And since I already said that these two genomes should be rather similar, it also implies that they have rather same size, right? So this is not a very harsh restriction, you could say, right? So we can imagine this is how they are related, right? Two genomes, and they have some common ancestor fairly recently then, right? So they haven't diverged a lot. From each of these genomes, we now collect k-mers, right? Of length k, which is actually unnecessary to say, right? Because it lies in the phrase k-mers that they are of length k. So we now, and this we have done, right? We have done this if you go back to module 3, we collected k-mers from genomes using the Jellyfish software. So we can now easily collect k-mers from both these genomes. And I also mentioned this one because this is something you see in the paper. The alphabet is denoted capital sigma here, and in our case, it's DNA alphabet. But it could have been amino acids as well. And then the size of the alphabet, which is this, right? The absolute value of sigma, that's 4, right? Because it's 4 letters. So I only mention this because this is something you see in the paper, right? And here is a quote from the paper. For nucleotide sequences, MASH uses canonical k-mers by default to allow strand neutral comparisons, right? So remember this. And we know what canonical k-mers are, right? Go back to module 3 if you don't remember. So we collect the canonical k-mers from each genome, or actually, yeah, we will see how we do this. But think of it in this way, right? So Jacquard index, what is the Jacquard index? It's actually a quite simple index or measure, and it measures the similarity between two sets. So think of A and B as two sets, and these can be sets containing all kinds of elements, right? It doesn't have to be k-mers like we are looking at in this context. It could have been numbers, it could be names, it could be anything, right? So this is a very, very general idea. And what is the Jacquard index? It is the size of the intersection, right? This is the intersection, and this absolute values indicate the size of this set divided by the size of the union. So what does a Jacquard index sort of measure? Here I have one set A, right? Indicated as a ellipsis here. And then if the set B is similar over here, we see they have an intersection here. This is the intersection, right? They overlap. Some elements of A are also elements of B. But rather, many elements in A are unique to A, and also many elements in B are unique to B, but they have something in common here. And this means, this the numerator here, the size of the intersection, that's the area here, right? The intersection area. While this union is the total area if you have both the yellow and the blue here. So that's a much bigger area, right? So here we can see that the Jacquard index is like 0.1 because this area here is like 10% of the total area. Over here we have the same set or some other sets that I call A and B, and this time they overlap a lot, right? So here the intersection is quite big and the union is actually smaller, right? And this means the Jacquard index is now much bigger because now the numerator here is quite big and almost as big as the denominator. Right? And you can see that if the Jacquard index is 0, it means the sets are not overlapping at all. There is no intersection and they are completely unique sets. On the other end of the scale, if the Jacquard index is 1, it means the intersection is actually the same as the union and the two sets are identical to each other. So the bigger Jacquard index, the more similar the sets are. We can now think of k-mers, the set of k-mers as these sets, right? We have collected number of k-mers from one genome, a number of k-mers from the other genome, and then we can compute the Jacquard index based on how many k-mers they have in common. So collect all the distinct canonical k-mers from both genomes, and we assume this is n, right? Because if k is large, and this is also something we saw in module 3, if you have a rather long k-mer, it's very unlikely that you see it twice in at least in a random genome. In a biological genome, there are some k-mers who will be seen twice, but they are not very many, right? They are the repeated regions, and they span just a smallish part of the genome. So this is almost always true, right? If you have a genome of size n, then you have approximately n unique k-mers, given that k is a little bit large, right? And then W indicates the number of k-mers that are common between these two genomes. That is what is meant by identical here. I mean, you collect k-mers from G1, collect k-mers from G2, and then you see that W k-mers are shared between these two genomes. The total number of k-mers is this one, 2n minus W, because you count all the n k-mers in the one set plus all the n k-mers in the other set, that's 2n, And then you have counted the intersection twice, right? So you have to subtract 1 times the intersection to get that also once. That's the size of the union. So actually the Jaccard index is this, right? The size of the intersection, W, divided by the size of the union here, 2n minus W. Remember this formula here. We will use it in 2 slides. And also, this is something we could have done by using jellyfish, like we did in module 3. We could have collected all the k-mers from one genome, all the k-mers from the other, and start comparing them, right? So in theory, we know how to do this, compute the Jaccard index between 2 genomes. Mash distance. What is mash distance? Well, then we have to recapitulate from introductory bioinformatics. What is an evolutionary distance? What is an evolutionary distance? It's defined as the expected number of mutations per position in the genome. Per position, right? Expected number of mutations per position. Yeah, go back to bin 210 to repeat this if you don't remember. We also have approximate evolutionary distance if we use the what is called the ROM or model, or the p distance, because this expected number of mutations is impossible to actually observe. This is impossible to observe, but this is sort of what we try to compute, right? What we actually observe is the number of differences. So, so the raw estimate you can see of this true evolutionary distance is this p distance that we also call it. Expected number of differences per position. And notice the number of mutations and number of distances is not the same, because you can have mutated back and forth several times. Right? The same difference can have been changed over and over again. So the number of mutations is always bigger than the number of differences that we now observe. So if we have a raw distance d, it's the same as saying that the probability is d that these 2 genomes differ in one given position. Right? You sort of pick one. Remember, these 2 genomes come from a common ancestor. You pick one position on that common ancestor, and then you locate that same position on G1 and the same position at G2, and D is then the probability that they differ. So D is usually a very small value, right? Or it's much closer to 0 than to 1, right? The probability is always between 0 and 1, but this is close to 0, or like 1% or 10% or something in that range, right? Not 90%. It's always low. Of course, if G1 and G2 are wildly different genomes, right? If this is a bacterium and this is human, then D is big, but then we are not, these cases we are not interested in, right? It has to be fairly closely related genomes, and then D is always sort of smallish. The expected number of differences in a k-mer is then just k times D, right? Because D is the probability of a difference at each position. And in a k-mer, there are k positions. So the expected number of differences in a k-mer must be just k times this probability. And then in this paper, they use a Poisson model, saying that the number of differing positions in k-mers, if you collect the k-mers from this G1 and G2 at the same sort of region of G1 and G2, the number of differing positions in this k-mer is Poisson with parameter lambda, which is actually k times d. And why is not this a binomial? Well, actually it is. This is actually a binomial variable. This is coin flipping, right? You flip the coin k times, and each time you flip the coin, the probability of head is d, right? The probability of difference. How many differences will you see after flipping the coin k times? But if you go back to module 3, we also talked about this relation between binomial variables and Poisson variables. And very often we use the Poisson as an approximation to the binomial because it results in simpler mathematics. So it's purely convenience. And if you replaced in the following now, if you replaced all the Poisson formulas with the binomial formulas, you will see that, or if you try to compute something, you will see you get the same results, at least to the first 5 decimals or something like that. So it's a very close approximation. So here is the here's actually the formula, the probability mass function, as we say, for the Poisson distribution, right? The probability of m differences, if it's a Poisson variable, it follows this formula here. So you can see the lambda is in here to the power of m, and then it's the exponential function here, and then it's m faculty in the denominator here. So this is taken directly from the textbook in statistics. Then we see that if we now compute the probability of m equals 0, plug in m equals 0 in this formula here, and your results in this very simple here, only e exponential of the minus lambda, and then we just replace lambda with kd over here, so we have this simple expression. This is the probability of having 0 differences, right? The probability of having no differences, m equals 0, right? Having no differences, if we collect a k-mer from G1 and the same k-mer sort of, or k-mer from the exact same position in G2, this is the probability that these two k-mers are identical. And we can see it depends on this d, right? The distance. So if the distance is small between the two genomes, this probability is high. But if the distance is big between the genomes, this probability is small. And that sounds reasonable, right? The more distantly related the genomes are, the less likely it is that two k-mers coming from the same region is the same. Something may have, if they are far from each other, things have mutated, right? So the k-mer starts to not be identical. So the k-mers with no differing positions, they are the ones who are identical. And we know that if we call this W, right? At least what we observe is W, right? These are the number of k-mers who are identical. And now we know that expected number of such k-mers must be the probability of this happening times the number of k-mers we have. So again, this is like coin flipping, but now here's the probability of having no difference. And if you multiply this with how many k-mers you have, then you have approximately what you observe number of identical k-mers, k-mers without differences. So notice there is an approximation here because this expected value is never exactly what you observe, right? Because this there is a variance here, right? But so this is the peak, right? This is where the distribution has its peak, and this is what we observe, which is always nearby the peak, but it could be a little bit above or a little bit below. So that's why we have this approximate here, but it's quite a good approximation usually, at least for big N here. And then we can just rearrange this a little bit to get this one. We just divide by n on both sides, you can see that. So the reason I do that is that this exact formula is what you find in the paper. So remember this one as well. And now we combine from the previous two slides. We have the formula for the Jaccard index 2 slides ago and the formula from the previous slide here. And now we just solve for D. What you actually do is you solve this one for W first. So you get an expression for W expressed as depending on J and N, right? And then you just plug that in for W here and solve for D. And then you get this formula here. And again, notice there is an approximate here because of the approximate here. So the evolutionary distance between the two genomes can be described in here like this, depending on the K, which is the size of the K-mers, and the Jacquard index. Can you see that? But no W. W is no longer in here. And now the MASH distance is defined as actually this right-hand side here. This is the MASH distance. And we can see that it's an approximate to the evolutionary distance, right? But it's not exactly the same thing. But this is an approximate to the raw evolutionary distance. So why do we want a formula like this? Why would we get rid of this W, for instance? We need now to compute this Jacquard index, right? Because that's part of the formula here. This one is we know, right? That's the size of our K-mers. But this Jacquard index we don't know. Wouldn't it be have been easier to compute this W? Well, in a sense, it's easier, but now we turn our sort of attention to speed. How can we compute this MASH distance in the fastest possible way? And this is really where this idea is shining, I would say. The min-hash idea. And this is an idea that comes from actually from one of the internet search engines that is, which is no longer with us, I think, but it was once before Google stole the whole market. This was one of the search engines that spawned this idea here. So the idea is to not compare all the K-mers from G1 to all the K-mers of G2. Because that's what we need to do to compute this W, right? We need to first collect all the K-mers from one genome, collect all the K-mers from the second genome, and then start to compare every pair of them. And this is horrible, right? If you have 1 million K-mers from the first one and 1 million from the second one, then you have 1 million times million comparisons. And this will take a long time to do even on a fast computer. The point is that the Jacquard index can be estimated very well by looking at subsets of K-mers. We don't need to compare all K-mers in order to compute this Jacquard index. And the question is which subsets to look at. And this is perhaps not obvious at once, but it's not very difficult to sort of get this idea once you see it. Should we sample at random from both genomes? No, this turns out to be really a silly idea to do. And I think I will try to demonstrate it shortly, why this doesn't work at all. It works only if the random sample is almost the size of the two genomes. And then you haven't really, if you have a subset which is almost as big as the set itself, then no time has been saved, right? The much better idea goes like this. Sort all the K-mers, for instance, alphabetically. Sort them alphabetically, and then only compare the S first K-mers from both genomes. So you sort all the K-mers in both genomes first, and then you compare only the S, the subset of size S, right? The S first K-mers from both genomes. And if these two genomes are very similar to each other, the first K-mers after sorting will also be very similar to each other. Imagine the two genomes are identical. Then, of course, the K-mers you have after sorting in one genome is exactly the same K-mers you have as sorting in the second genome. The sorting of all the K-mers, however, is sort of slow. So there is still some way to optimize this. But before we actually go to seeing how this min hashing is working, I want to show you an example in R, just the difference between these two ideas here of sampling at random and sorting first. So I prepared a small script here in R. And let me just briefly tell you what it does. I sample at random a set A consisting of 1,000 integers from 1 up to 100,000. So it's just randomly collect samples at random, these numbers, 1,000 of them. And then I make a set B, which is also 1,000 numbers, but I make sure that the first 200 values in A are also in B so that they have some overlap here. Right? So now we have some overlap, right? Guaranteed. And then I compute the Jaccard index straightforward using both the full set A and the full set B. So this is sort of the big job that we are trying to avoid, but this gives us the exact Jaccard index. So if I run this one here, you can see I have 1,000 numbers down here, and then I run this one here. I have another 1,000 values here, and they are not in the same order, right? So they are in completely random ordering. And then I compute the Jaccard index by taking the size of the intersection dividing by the size of the union. And you can see in this case it's 0.11 something, 11%, right? Jaccard index. So they have some overlap, right? The intersection is like 200, and since each of them are approximately 1,000, or each of them are exactly 1,000 long, the sets have size 1,000. So you have 200 divided by, yeah, the union is a little bit less than 2,000 though, because they share this 200, right? So that's why the Jaccard index is a little bit more than 10%. If we now sample at random a subset from A, right, a capital A, and I call this lowercase a, just sample at random 100 of the values, 10% of the set, and the same for B, and then we compute the Jaccard index. Look at it down here. Look at it. It's very, very small, right? It's only 1/10 of the actual Jaccard value. And if I do it again, I can sample again, get slightly different values. But this Jaccard value is still very much too small. Because the probability of sampling, when you sample at random, just a few numbers from each set, it's very unlikely that you sample something which is in the intersection, right? And here it was dramatically small. So you can repeat this over and over again and see it will never be close to the true value of 0.11. However, if you sort the subsamples and then sample 100, A and B, and then you can look at the Jaccard index. Look at this, it's much closer. And we can do it again. So now, and it's the same because there is no longer a random sample, right? We sort, so each time we sort, we get exactly the same values. So if you want to repeat it, you have to sort of repeat the whole running of the sets, and then we can completely different values. Whoops. Sort A, sort B, and then the intersection here. Yeah, so now it was a little bit less than 0.11, but it's around that value, right? So this illustrates how much closer you get to the true Jaccard index by doing it this way compared to random sampling. So the idea that makes this different from what we actually saw by sorting is the use of hash function, the min hash idea. A hash table. What is a hash table? A hash table is actually a data structure made for fast lookup. If you imagine you want to store the phone numbers. This is a typical example. You have a name, and for each name you have associated a phone number, right? And then you want to look up the phone number given a name, right? I give you a name and you want to make a fast lookup. What is the phone number of this person, right? Then you typically have the keys that we call, that's the sort of information that you have, the name. And then you store the phone numbers in an array, in a vector. Think of it as a vector, right? The point is that we now have what we call a hash function that takes the text, the name, or it could be any text, takes a text, and for each text, each unique text, it produces a unique number. And this number is now exactly the row in the vector where you have stored the phone number for this person, right? So each new name gets a new number from this hash function, and if the same name appears 2 times, it also gets the same number both times. So it's not a random number. This number is sort of computed from the letters here in some smart way. And exactly what this how this hash function is built is not something we're concerned about now. Making good hash functions is really an art. But we just think of it as some function that is given to us, that for each new text we put into the function, it returns back to us a number, which is a row in a vector, right? And this makes lookup extremely fast, right? You don't have to start searching through this vector. You can go directly to the position where you have the phone number. So each object, in our case a k-mer, so replace the names here with k-mers. They are also text, right? Each k-mer is converted to an integer by a hash function. That's what we see here. And then the object is stored, or the information about the object is stored in cell I in this array, right? The integer that so this integer we get is an index, right? It's an index indicating which element in this vector we should now look into. So this makes the lookup extremely fast. So this in address I is what we call the hash. So think of it just as a number. A hash is just a number, an index, an integer, right? And each new text here will get a new hash value. And such hash function, in order to make this lookup really fast, this must be really fast functions. So they don't sort of spend much time computing this number given the text. The cost by doing hashing is that you're not guaranteed that this hash function will use every row in this vector. So if you store the phone numbers of 1,000 persons, you need a vector of more than 1,000 elements, because some rows here will not be made use of. And that's sort of the cost of making this hash function fast. Yeah. You should take a course in algorithms and data structures to really get an idea of what hashing is all about. But hash tables, or hashing, is a technique we use for very fast lookup. So this is capital O1 algorithm, the fastest you can ever have, right? Because once you have the name of the person, it takes one lookup to find the phone number. Right? There is no searching through the vector. So this mean hash is now used to sort the k-mers. In the mean hash, we use the hash value. We don't sort them alphabetically. I only use that as an example of how to sort, but we can just as well use the hash values to sort the k-mers. And those are extremely fast computed, right? Because these hash functions are made for super fast computation. So for each new k-mer, zap, you have the value of it, the hash value, and then you just sort the k-mers. And then we just store the S smallest, or we could have stored the largest, it doesn't matter, hashes. And that's what's called a bottom sketch then, if you store the smallest hashes, right? You just have to choose one or the other. And it's like sorting alphabetically, right? After sorting, do you look at the first S elements or the last S element? Doesn't matter. So a sketch is now a subset of hashes, and we decide the size of it, right? The S. And we will do some sketching in this course now. And then they say here in the paper that for a sketch of size S and a genome size N, a bottom sketch can be efficiently computed in capital O n log S time by maintaining a sorted list of size S and updating the current sketch. So actually when you start collecting the k-mers, right? The first, let's say we have set S equal to 1000. You want to store the 1000 smallest hashes. Okay, then the first 1000 k-mers will all be stored in our sketch initially, right? But then as you start to look at the 1001st, 1002nd, 1003rd, and so on, you just replace, if the new hashes are smaller than the biggest of the 1000 already stored hashes, then you just replace that, right? So that the 1000 smallest hashes are found. So you just have to go through all the n k-mers and then a little bit more than that. And it also says that the further you come into the set, you can imagine you start by the first 1000 k-mers. Okay, so all of them will be stored in a hash. But then once you have collected like 1,000,000 k-mers, you have probably found almost all the smallest ones, right? So only a few of the last ones will replace some of the already found ones. So actually, it turns out that this is almost linear in this capital O of n, nearly linear. You can plot and see that this term here doesn't contribute with almost anything. So it takes the time it takes grows linearly by the size of the genome, or the two genomes then. So if you double the size of the genomes, this double the time it takes. And that's much faster, right? Compared to if you start to compare all the k-mers to each other, then it's capital O of n squared, right? This is capital O of n. Super much faster. So here's a drawing from the paper. So here you can imagine we have the blue and the red genome, right? We collect the k-mers and then we run them through this hash function. And here is the set of hashes from the blue genome. And here is the set of hashes from the red genome. And then from the blue genome, we collect the 5 smallest hashes. These are the filled dots here. And from the red genome B, we also collect the 5 smallest hashes, which are filled dots here. And then once we have all the smallest hashes here and all the smallest hashes here, we start to compute the 5 smallest hashes among these 2 sets of hashes. And those are the 5 with crosses on, right? Crosses on here. So the 5, so this is in the middle here, the 5 smallest values if you collect all these and all these. And then you will see that this 82 is member of both, right? Sides. And that's the one you see here. It's in the intersection, right? The hash 82 is here. And then we can, from this picture here now, infer that the Jacquard index here is 0.20, 0.20, because there are 5 hashes. That's sort of the union, right? And the intersection is 1 out of 5, 0.2. So 1 out of the 5 with crosses is in the intersection. And you can see that if we had collected all the k-mers, it is actually of course, this drawing is made sort of perfect. So if you collected all the k-mers in the intersection here, you will see that this is also 1 out of these 5, right? So this is how the is approximated. So a few words about sketching read sets in the end, because up to now we looked at genomes, right? But this idea can also be used for directly from the read sets. You don't need to assemble the genomes, because the k-mers we get from the genomes should be the same k-mers you get from the reads. Can you see that? Only you see the k-mers over and over again in the reads, but they are the same k-mers. And what we need to do when we consider reads instead of a genome is that we have to filter out k-mers with low frequency, and we know why, right? If you go back to module number 3, you will see we talked about this there, because k-mers should appear around k-mer coverage number of times. Right? If you k-mer coverage of, let's say, 50, then k-mers that occur only once or twice, they are probably error-prone k-mers. They have some sequencing error in them. And these k-mers we should, of course, not collect. We don't want to collect the k-mers with errors in them. So that's why we filter out k-mers with a low frequency. And this only applies to read sets, because when you look at genomes, right, assembled genomes, then all k-mers will have low frequency. Think of that. So you can't use this for genomes, because then you throw away everything. Well, a Bloom filter is used to quickly eliminate the k-mers occurring less than C times. So that's, again, a technique to speed up things. And this limit C is set by the user, and by default is 1, so you don't really throw away anything. And this is fine when you look at genomes, as I said, then you have to use this value 1. Otherwise, you end up with almost nothing. Only the repeated regions will contribute with something. That's silly. But for read sets, this is sensible. Bloom filter, I will not talk very much about it because there is actually a movie here by Rob Edwards. We have seen some of his films before. So I just urge you to look at this YouTube video here and hear what Rob Edwards has to say about Bloom filters. The point is that this is a very quick way of eliminating low frequency k-mers, you could say. But so I think that for our course, we don't want to dig very deep into this technical stuff. We only need to understand why it's a good idea to do this. But exactly how it's done, it's for those of you who are curious. Have a look at this video.